All right, this is the review for semester 1 of Algebra 2. Problem number 22, page 7. Page 7, problem 22, simplify the expression fully. So this is a radical expression. It has an index of 3 in the radical. And the radical is a grouping symbol, so it goes all the way to the end, and all of this is inside the radical. If you are going to copy over a radical, make sure that you pay attention to where that top part starts and stops, because it is a grouping symbol, and that is very relevant, like where you put parentheses matters. So the first thing I'm going to do is take a look at this negative 32, because the cube root will apply individually to each of these factors. I could even, in fact, rewrite this as individual cube roots if I wanted to, if it helped me understand that is valid. Just like exponents distribute across multiplication. If there was any addition, I could not do this. If there was any addition in this problem, I absolutely could not do this. This does not work when there's addition, because addition's down here, then repeated addition is multiplication, and repeated multiplication is exponents. So this distributes along that, and this distributes along that, but you can't skip a level. You can't do it when there's a sum inside a radical or an exponent. So just don't do it. But here we can distribute this radical across all of this multiplication and do each one at a time. Negative 32 can be factored in my little factor tree. I know a 2 comes out, and I have negative 16, and another 2 comes out, and I have negative 8, and another 2, and I have 4, and another 2, and I have 2, and another 2, and I have negative 1. Interesting. Okay, so I can rewrite the square root of 32, or sorry, the cube root of negative 32 as the cube root of 2 to the 1, 2, 3, 4, 5th power times the cube root of negative 1. That's just one way to think about it. The other would be to give each of these a negative. It's fine, whatever. It all works out to the same. I like to separate the negative as its own thing. Now the cube root of negative 1, if we graph the cube root function, which you did on page 1, the key points were negative 1, and positive 1, positive 1. Negative 1 is its own cube root. So the cube root of negative 1 is negative 1. The cube root of 2 to the 5th is going to be 2 cube root of 2 squared. 3 of them can come out, but 2 are left inside. So when I replace this piece right here, I get, so I have negative 7, I get the negative 1 times the 2 and the cube root of 4. That is what's here. Let me color code that for you. So this whole expression became this expression. That is fully simplified for cube root of negative 32. So now I'm going to continue to work on each part individually. The cube root of x to the 4th is x cube root of x, because 3 of them come out as 1 and 1 is left inside. So that's this piece. Cube root of y is just the cube root of y. And the cube root of z cubed, though, this one, everything comes out and it's just a z, right? So now I need to be able to see all the individual pieces. Negative 7 times negative 2 is a positive 14. I also have, so I'm going to grab all the pieces that are outside my radical. Let me do it in purple. So this is outside, this is outside, this is outside, and this is outside. All of those are outside my radical. So 14xz, yeah? And then my cube root, everything inside, 4xy. So that is one way to see what's happening here. We don't have to write the multiplication, but I want to show that that is all multiplication. And my radical needs to encompass all the way to the end of 4xy, because all of that is left inside. So that's one way to handle this. You're definitely going to have to factor your negative 32. That's the key. Simplify the expression fully. This is a bit of a mess. So let's make room. First thing I'm going to do is change my radicals to exponents. That makes this have an exponent of 3/2, right? A radical was a 1/2 exponent, and I can multiply exponents raised to exponents. So that becomes 1/2. Then when I distribute that exponent to each of the factors inside, I get x to the 9/2, y to the 3, because 2 times 3/2 is 3. So that's my numerator. Now this fourth root becomes a 1/4 power. This cube root becomes a 1/3 power, and then mixing with the -2 is -2/3 power. If I distribute the 1/4 to each factor, this becomes x to the -1/4 times y to the -2/12. My next step, well, I could simplify the 2/12 to 1/6 if I wanted to. Makes it a little simpler. 2/12 -2/3 times 1/4 equals -2/12 equals -1/6. All right, these negative exponents, I'm going to change which side of the fraction bar they're on. If I divide by something with a negative exponent that tells me to divide, that's the same as multiplying. It's like undoing. So I have x to the 9/2 times x to the +1/4. This whole thing gets to go into the numerator, but all that does is take away the negative in the exponent. And then I still have my y cubed, right? And my y to the +1/6. And now I have nothing left in the denominator. So there's always a factor of 1 just hanging out, but we can even make that go invisible. There is no more denominator. So my next and hopefully last step will be to add these exponents, because if I have this many x's and this many x's, that is this x raised to the this many plus this many. So it's going to be x to the 9/2 plus 1/4. I'm going to have to make this force, adding fractions, common denominator. Here we go. I need a factor of 2 in addition to make the denominator 4. So now I have 18/4 plus 1/4. That'll be 19/4. And then my y, I have 3 plus 1/6. To give this a factor of 6, I need to multiply by 6/6. And now this is 18/6 plus 1/6 is 19/6, which doesn't simplify. And that's the whole answer. Pretty sure that's right. -2/3, yeah. -2/12, yeah. Yep, that's right. Now I could always type this into, well, all right, this is a little bit tricky to type into Desmos and check, because functions with combined x's and y's is not really super great. It doesn't handle it well. So anyway, just trust me. Now this one's even more fun and a lot less detail and no fraction addition, because everything is multiplication. So when I multiply the tops and I multiply the bottoms. So, but first I need to deal with these negative exponents, because if I can't multiply I can. Well, one way to do that would be to say, when I multiply bases raised to exponents, I add the exponents. So I could see that this would become 2 to the a to the 0, and a to the 0 is just 1. So the a's go away. The other way to see that would be to say, to make this have a positive exponent, I would put it into the denominator instead. A to the positive 1. And then I can see that a over a simplifies to 1. So in a couple of different ways I can see there ain't going to be any a's left over in our problem. Now the 2b to the negative 1, if I wanted to get rid of that, I would need to move the whole thing that's in parentheses. This exponent is on the parentheses, so everything goes with it. If it weren't, only the b would move. But with it in parentheses, the whole thing moves, and I have a 2b to the positive 1 here. And then I can see my b and my b will cancel. Or in my denominator, maybe I have a 2 to the negative 1 and a b to the 0, which makes 1. Either way, I don't have any b's left over. Oh my goodness. And this 2 has moved to the top, so the whole thing is equal to 4. Just 4. All of that, doesn't matter what a and b are, actually as long as they're not 0. A can't be 0 because this is technically a denominator being raised to the negative 1 power, and b can't be 0. So the domain of the situation is a can't be 0 and b can't be 0. But otherwise, no matter what they are, the value you'll get from this expression, which is too messy to see, is 4 every time. Crazy. All right. Find the product of the following functions and simplify into standard form. So I'm going to multiply these two things. Well, multiplying two things with pluses and minuses means I'm going to use my area model. 5x minus x to the 4th times x to the 5th plus 2x to the 4th. I'm going to get 4 pieces, and I'm not sure any of them are going to match, but we'll see. This will be 5x to the 6th, because this is x times x times x times x times x, and then times another x. So 6 total x's, and a factor of 5. This one will be 10x to the 5th. This one will be negative x to the 9th, right? 5 x's times 4 more x's, and then a factor of negative 1. And then 2x to the 4th minus x to the 4th. Oh, but I'm multiplying. No, it's times negative x to the 4th. Don't think about it as minus, sorry. 2x to the 4th times negative x to the 4th is negative 2x to the 8th. Multiplication, keep that in mind. Which means in fully standard form, I need to find my biggest exponent, which is negative x to the 9th. And then my next biggest is minus 2x to the 8th. And then my next one is going to be plus 5x to the 6th and plus 10x to the 5th. The result of multiplication is the area inside. When we were doing division, we put our numerator inside and divided by the outside edges. So area model, keep in mind what you're starting with and what you're going for. Identify and circle the functions shown in this graph. Write a sentence to explain. So how do we know which function this is? One of the biggest indicators is going to be your end behavior. If we assume we can see the whole function, this end behavior that goes up and up is just like a quadratic or a 4th degree or a 6th degree. It is even degree. And when x is very positive, y is very positive. So there must be a positive leading term or leading coefficient, whichever. It must be positive. So when I come over here, I'm looking for the degree. Checking to make sure each of these is in standard form, I can look for that first coefficient. That's odd, no good. Or first degree, I'm sorry, first term. That's odd, no good. Ooh, that one's even, check. And that one's even, check. But that positivity, the fact that when x is really big, y gets very positive. Even when x gets very negative, y gets very positive. This must be my function because it is positive x to the 4th. That is no good. That would flip the whole thing upside down. We can double check that we like the answer by looking at its y-intercept, because in standard form, the y-intercept is the low-hanging fruit. This is plus 0, and look, in fact, its y-intercept is 0. So that is a good double check to make sure we understand that it must be that one. But again, we're looking at the end behavior to tell us all of this stuff about the degree and leading term. Okay, that was page 7.